So, we start our third session on the carrier transport in nano MOSFET devices and MOSFET non-classical MOSFETs. So, we continue on some effects of short channel lengths on carrier velocity. We just began on this last time. The three aspects which we will be discussing will be, one is the velocity saturation effect on the drain current, and then a quick look at what is the implication of ballistic transport and velocity overshoot effect, whether we should worry about that also we will discuss. For silicon, we will see how good is important is the velocity overshoot is there. Then we will also discuss injection velocity, which is ultimately the one which controls the drain current in short channel devices. Now, before we go into that velocity saturation, we take a quick look at the velocity versus electric field characteristics of the carriers. I use the word carriers because this sort of curves hold good both for electrons and holes. What I am showing is mainly for electrons right now. Similar argument can be extended to the holes also. Now, in thermal equilibrium, when you do not apply an electric field, the free electrons are moving in random directions because they have the thermal energy. They move with the thermal velocity, which is about 10 to the power of 7 centimeter per second. Okay. Now, even though they are moving, there is no current flow because they are in random motion and each of them cancel in all the directions. So, there is no net current flow. Now, when you apply an electric field, the electrons have an additional component in the direction of the electric field, that is, it moves towards the plus terminal opposite to the electric field direction. So, it has a component of velocity. So, the carriers move in that particular direction directed by the electric field. If it is holes, it will move in the direction of the electric field plus to minus. If it is electrons, they move from minus to the plus. So, now this component is superimposed on the thermal velocity. So, you get the current due to the velocity of these electrons, which can be expressed in terms of electric field and collision time. What is collision time? When the electrons move in the particular direction, they get scattered by the lattice atoms. They get scattered by various effects. So, in a time tau m, there will be collision. So, the velocity the electrons get accelerated by this force q into E. Q into E is the force on the electrons, E is the electric field divided by m star. M star is effective mass of electrons because you talk of movement of electrons in the crystal, not in the free space. So, this is the acceleration. Acceleration into time of collision gives you the velocity. Acceleration into time gives you the velocity of the carriers at the time of collision. So, that is the maximum velocity that it gets. You can say there are different electrons which will suffer different accelerations and or different collision lengths and collision times. So, what we talk of this velocity will be an average value for all the electrons put together, which gives rise to current. Now, this thing whatever we write here, we usually express as mu into electric field, where mu is actually q tau m divided by m. From here, I just pull out this electric field term out and call this term as the mu, that is the mobility. Now, you can see here there was an assumption that when you change the electric field, the collision time was not changing. So, that is why this mobility is constant. So, V is proportional to electric field and velocity field characteristic will be linear when the electric field is low. At higher electric fields, since the acceleration is more, the time of collision will reduce, because the distance between collisions is same, the time of collision or collision time will get reduced. So, that means the mobility actually gets reduced, but electric field is increasing. So, the velocity field characteristic does not increase linearly, but it becomes nonlinear. Okay? This is because of collision time reduction. So, even though electric field is increased, it does not increase velocity, does not increase as much as you think it should. When you go still to high electric fields, you can see that the velocity will become higher and higher, and it will become comparable to the thermal velocity, which is there even due to thermal energy. So, total energy of the electrons now becomes thermal energy plus this additional energy which is absorbed from the electric field. Now, the kinetic energy, which you call it as half mv squared, is related to the temperature or kT. So, once you say that the kinetic energy has gone up because of the thermal energy and the energy absorbed by the electric field, in fact, finally, the energy, kinetic energy, net energy is this one, due to the energy absorbed from the electric field. So, you can say that is, it looks as if the temperature of the crystal has gone up, or temperature of the electrons has gone up. Even though crystal temperature is room temperature, the electron energy is higher by this amount. So, you say that they are hot electrons. Electrons are not really hot, it looks as if they are hot because their energy is much more than that of thermal electrons. Okay. So, when they collide, so you can see now these hot electrons have addition energy over and above the regular thermal energy. So, when they collide with the lattice atoms, they excite the lattice into a new vibrational mode, which has large cross section for intercepting the more electrons. In other words, what I am trying to point out is, these electrons, when they collide with these lattice atoms, because they have large energy, they create extra vibrational energy in the lattice. So, if there is extra vibrational energy, the chance of collision of these electrons becomes more. For example, if the atom is moving like that, the cross section of that movement is much larger. So, what happens is, almost all the electrons collide and lose the energy. So, the maximum energy that is acquired by that is decided by that velocity that is achieved by that, and that velocity is equal to the thermal velocity or close to that. See, when the velocity has become equal to thermal velocity or close to that, the energy is almost much large compared to thermal energy. So, at that point, what is the velocity acquired? That is close to thermal velocity. It is not exactly equal to thermal velocity, but very close to that, slightly less than that. Still, we can say V is saturation, that is velocity at which the maximum velocity is reached, is the saturation velocity. So, what happens is, if I keep on increasing the electric field, initially linear, non-linear because of the collision time decreases, finally, velocity saturates because all the energy that is acquired within that collision time is lost to the lattice. So, within that time, it is whatever velocity is acquired is very close to the thermal velocity, which is the limiting velocity of the electrons. It can't go beyond that, because the entire thing is absorbed by the lattice. Okay. So, this is the principle of velocity saturation. Is basic semiconductor devices. This discussion comes. For completeness sake, I just brought this one into. So, what happens in the case of MOSFET? So, remember that linear, non-linear, saturation. If the field is and that saturation velocity is about 10 to the power of 7 centimeter per second for electrons. For holes, it is about 6 times 10 to the power of 6 centimeter per second. Now, if you take a look at the velocity saturation effects on the short channel MOSFET, what will be the electric field? the electric field along the y direction, that is from the source to the drain, in that region there is a voltage drop equal to gate voltage minus threshold voltage, that is the channel potential which we have discussed earlier. So, voltage drop across the channel from between the drain end and the source end, once saturation current has reached, is this VGS minus V threshold. Now, you can call or you can think of how much will be the electric field, that is whatever voltage drop is there divided by channel length, that is average electric field. So, now you will see as the channel length becomes shorter and shorter, electric field becomes larger and larger. That means, if the electric field is larger than about 30 kilovolts per centimeter for electrons, the velocity saturates to 10 to the power of 7. So, what you are telling is this 30 kV per centimeter can be reached very easily. See, for example, even if you take a number like 1 micron channel length, if the VGS minus V threshold is 3 volts, okay, 3 volts divided by 10 to the power minus 4, that is 30 kV per centimeter. So, even there you can have velocity saturation. You can see if the channel length is smaller, even if the threshold Vg minus V threshold is 2 volts, 1 volt, you will have the velocity saturation. So, when you go down to 0.1, 0.2 micron channel length, definitely there will be velocity saturation, and that value will be 10 to the power 7 per centimeter for electrons, and whole velocity saturates at slightly smaller value because of its higher effective mass. Okay. Now, let us see how this will change the drain current. If we are operating in this region where the velocity is proportional to electric field, the Ohm's law holds good, and there we said it is a square law. IDS is equal to VGS minus V threshold whole square into some constant which depends upon mu C oxide W by L. Here, let us see that. So, due to high electric field, I just take a look at the drain current in the scaled down MOSFETs, that is short channel lengths, everything reduced in size. Due to the high value of electric field in the y direction, that is along the channel length, okay, the velocity of carriers will be saturation velocity. Now, we have assumed that electric field is very high everywhere, that means velocity saturation will be there everywhere. So, if you take the current at the source end itself, whatever current enters here will flow through the thing. So, we have written this formula, the drain current is width into charge into velocity, WQ into V. W is the width of the channel. Q is the electron charge here, 0 is implying that x or y equal to 0 here. So, Qn. So, WQ into Vsat is actually the drain current. This is the velocity saturation model, very simple. Now, if you write substitute for the inversion charge, okay, inversion charge is C oxide into Vg minus V threshold, that we have put here. So, the drain current now becomes W C oxide into Vgs minus V threshold into Vsat. Notice at this point the drain current does not depend upon the channel length. When the low field case, you remember that the drain current is W C oxide mu divided by L into Vg minus V threshold whole square. Now, here it is not square law, it is ID increases linearly with Vg minus V threshold, okay, and it is independent of the channel length, because the current is because the velocity is saturated. Velocity no longer depends upon the channel length, so it is independent. defined as delta IDS divided by delta VGS. Okay. When you differentiate that, this term goes off and you will have WC oxide into Vsat. So, you can see a couple of things here to be noted. Your drain current depends on the channel width, of course, but you do not want to make this large. The maximum that you can get will be decided by the saturation velocity, and of course, larger the C oxide, larger will be the current. That means, thinner the oxide, more will be the current. So, will be the transconductance. In all the integrated circuits, you would like to have best transconductance. That means, the velocity should be highest, and you get that. Why do you need best transconductance? Because the driving capability for a given change in gate voltage is maximum if transconductance is maximum. Okay. So, ID and GM are independent of the channel length. That is one thing to be noted. The transit time, that is the time required for the electrons to move from the source to the drain, that is length divided by velocity. Okay. And the transit time will control how much will be the cutoff frequency, that is 1 by tau t will be the omega t, f t is 1 by 2 pi tau t. So, high frequency transistors will have, of course, the shorter channel length, and because of shorter channel length you will get faster speed of operation, not because of improved velocity. Okay. Now, let us see whether you get the drain current independent of channel length when you go to smaller channel lengths. There is some experimental result which is available. This was reported in one of the thesis in the Stanford University PhD thesis. I think that these results are given by Intel. Very interesting. You see, you keep on reducing the channel length. X axis gives you the channel length, y axis gives you the saturated drain current, ID sat. That is after the drain current is large enough. So, as you keep on reducing the channel length, this is for different MOSFETs, shorter channel, shorter channel, shorter channel. You can see the drain current keeps on increasing because you are not in the velocity saturation region. The drain current is mu in this region is controlled by mu C oxide W by L into VGS minus V threshold whole square. So, because it is inversely proportional to channel length, the drain current keeps on increasing as you reduce the channel length. This is for the P channel N channel device. The bottom curve is for the P channel devices. Okay. But once you go down to channel lengths which are something like 0.2 microns and below, these are all the experimental points, they are all scattered, but on an average you can see that it is reaching constant. It is independent of the drain channel length, which almost shows that this is correct. Drain current is independent of the channel length. You can see that it is independent of channel length. Both N channel MOSFET and P channel MOSFETs show the same characteristics. There is a difference in these two numbers because of the difference in the mobility and difference in the saturation velocity, you can say. But if you calculate this, I think you have to watch very carefully. These devices have an oxide which is about 1.75 nanometers, okay, around that for these channel lengths, or 1.5 even. I have taken this number 1.75, and corresponding oxide capacitance per centimeter square is, okay, it is 2000 nanofarads per centimeter square. I am trying to find out if I substitute this C oxide and if I substitute it this V velocity saturation, do I get this number for electrons? See, what we are telling is, if there is velocity saturation, I can substitute Let me take VGS minus V threshold as 1 volt. C oxide is 2000 nanofarads per centimeter square, which is 2 into 10 to the power minus 6 farads per centimeter square. Okay. And V sat is 10 to the power 7. So, 10 to the power minus 6 into 10 to the power 7, that is 10. 10, the 2 is there. So, this product on this side is 20. Usually, they define the current as drain current per micrometer width of the channel. I have taken what they have given there in the experiment is per micrometer, W is 1 micrometer. So, when you substitute this as 2000 nanofarads, this is 10 to the power 7, product is 20, 20 into 10 to the power minus 4, 1 micrometer 10 to the power minus 4 centimeter. So, that 20 into 10 to the power minus 4 is actually 2000 microampere per micrometer. Okay. 20 into 10 to the power minus 4 is 2000 into 10 to the power minus 6, that is 2000 microamperes or 2 milliamperes per micrometer. So, what we are telling is, if there were velocity saturation, you would have got this current as 2000 microamperes per micrometer. What you get here is less than that, which would mean that there are two things. One is what you say is correct, that channel, the drain current is independent of the channel length, but the velocity is not velocity saturation. There is a different velocity which is smaller than the velocity saturation. Okay. So, that is what we get from here. Now, let us see what the model that we have taken here. What you have done is, you have taken the charge at the source end and taken the velocity is velocity saturation. Now, that would mean the current here is whatever charge is present into velocity saturation. If you go down along the channel, the velocity cannot increase beyond that point. Velocity is maximum is 10 to the power 7. So, if you say this is velocity saturation, here also there is velocity saturation, here also is velocity saturation. What happens to charge then? That would imply that charge also is constant, because ID, if it is 1000 microampere per centimeter square, it is the same thing everywhere, because current continuity. So, what we are trying to point out is, if you assume this model which you have written based on velocity saturation here, that would mean that throughout there is velocity saturation, that would mean that charge is throughout same, which implies there is no field in this region. Okay. If there is field in this region, plus here minus here, the charge will be keeping on decreasing. If charge is keeping on decreasing, velocity will be keeping on increasing. Okay. If the charge is not decreasing, if charge is constant, there is no voltage drop. So, the argument that we have put forward is not quite correct. So, what we are telling is, velocity saturation may not take place here, because charge is maximum. So, velocity is less than velocity saturation. As we move towards the drain end, charge keeps on decreasing, because there is a voltage drop here. Because charge keeps on decreasing, velocity keeps on increasing. You may have velocity saturation towards the drain end, not at the source end. So, what we are trying to point out is, at the source end, the velocity is less than the velocity saturation. So, I should calculate the current taking this same formula, but V is less than that velocity saturation. What is that velocity? We do not know right now, we will find out that. Okay. So, whatever I mentioned, I have summed up and put it here. The drain current formula in the velocity saturation model assumes that the electron velocity is Vs throughout the channel. This assumes that charge does not vary throughout the channel, which is not correct. So, from what we have discussed, we the charge does not vary means this is possible, there is no voltage drop, but there is a voltage drop across the channel if there is current flow. So, this will lead to the conclusion that velocity saturation is absent near the source end of the channel where the electric field is low, lower than the saturation 30 kV or so, and velocity saturation can exist only near the drain end. Now, let us examine that, quickly go through some of these things. So, this is the basic thing that is involved. So, experimental results, IDS is indeed independent of L, we are very happy, but this formula also holds good, except the charge when you take at the source end, the velocity is not velocity saturation, but some effective velocity which is lower than saturation velocity, but it is a function of saturation velocity, okay, and some other factor comes into picture. So, W C oxide into VGS Q and I am substituting here. So, all that we replace is this by V effective. Now, in V silicon, from the result that you have seen, this V effective is less than the saturation velocity. I will not go through this at this stage, but I will just point out that if you take gallium arsenide devices, that effective velocity will be even more than the saturation velocity, because of what is known as the velocity overshoot effect. If the electrons are injected to the channel suddenly to a high field, it goes through a transient phase where velocity gets much more than the saturation velocity, then comes back to the saturation velocity. So, that effect is dominating in gallium arsenide, whereas in silicon that is very marginal. Okay. So, it is always less than this. Now, let us examine this. There is one more term that I bring in here, that is the ballistic transport. Can there be ballistic transport of carriers in silicon? In gallium arsenide, question mark, I will not discuss that now. In silicon, what is ballistic transport? Normally, when the electrons get accelerated, they get scattered, okay, due to collisions with lattice atom or impurity ions, everything, whatever be the thing, scattering centers. Now, the ballistic transport is referred to the motion of electrons through the semiconductor material when collisions are completely absent. When will the collisions be absent? If the collision centers are far away. Okay. So, ballistic motion in the uniform electric field will be governed by the equation. The velocity there is acceleration into time. So, what we are implying is, if there is no collision, if the electron moves without collision, okay, the acceleration will be forced by the mass, the Q into electric field divided by mass. So, for example, if the electron is moving in vacuum, there is no collision, that is ballistic transport. The velocity will keep on increasing. That is why in vacuum tubes, the velocity of electrons is much more than that in semiconductors. That is why people are thinking of bringing back the vacuum tube for high power, high frequency operations. There is one activity going on when to bring in vacuum tubes into very high frequencies, terahertz frequencies. Okay. So, but if the time is t, if you take the velocity at that time is acceleration into time t. Now, ballistic transport will take place so long as the time is less than the collision time. There is no collision. Now, let us see what it is in silicon. This is something people have simulated from Monte Carlo simulation, etc. They have seen that for silicon, the average collision time is about 3 into 10 to the power minus 13 seconds, that is 0.3 picosecond, very small. Within that time the collision takes place. So, you will have ballistic transport in a time less than that collision time, there is no collision. You can use this equation to compute that is what we actually do. Okay. So, what is that length? Let us see. Let us say the electron is moving with the velocity of 10 to the power 7 due to ballistic action, average velocity 10 to the power 7, and the time t 3 into 10 to the power minus 13, what is the length travelled? That is 3 into 10 to the power minus 13 into 10 to the power 7, that is 30 nanometer. That means, if you assume that maximum velocity 10 to the power of 7 is present for the electrons, and within that collision time it would have travelled a distance equal to 30 nanometer. That means, there will be ballistic transport if the channel length is less than 30 nanometers, if the very much less than 30 nanometer. If the channel length is 30 nanometers and above, it will be governed by the scattering, that is the mobility and saturation velocity. Okay. So, what we are saying is there will not be any ballistic transport that is in silicon till it is about much less than 30 nanometers, say 10 nanometers, 50 nanometers. If you go, you can say there is ballistic transport will be there. So, you may not have velocities much greater than the velocity of saturation at the source end. That is the meaning of that. So, in silicon MOSFETs, pure ballistic transport will not take place until the channel length is well below 30 nanometers. Okay. We examined that to see if there is a chance of velocity higher than the saturation velocity. That is not possible. If you take gallium arsenide, again the simulation results have shown that the collision time there is 5 picoseconds, much larger. So, if the velocity is 10 to the power 7, I am taking the maximum velocity, it will not be that much, then the length travelled by the electrons before the collision has taken place is velocity into this time, that is 500 nanometers. What we are telling is, in gallium arsenide, the collision will be absent or scattering will be absent till it has moved 500 nanometers, 0.5 micrometers. Okay, which that would imply that there will be ballistic transport in channel lengths which are 0.5 microns. So, if the carriers are injected into that gallium arsenide channel in that short period of time before it gets scattered, if it is suddenly injected into the channel where their high field is present, it will get accelerated to high velocities higher than that of 10 to the power of 7. That means, in gallium arsenide you will have velocity overshoot effects, like transient effects in the LC circuits, etc. Okay. There will be overshoot effects will be there, because before it comes to steady state, the velocity goes over and above the saturation velocity, and that may give rise to your injection velocity much more than the saturation velocity. So, that is why in the case of gallium arsenide devices, you may encounter drain currents which indicate that the injection velocity of electrons is much more than the saturation velocity. That is because of the velocity overshoot effect. I have put it very briefly without going into details of that. The meaning is, sudden transient effects in gallium arsenide leads to that overshoot effect, because that has at least few picoseconds of time, whereas in silicon you do not see that, because it is less than much slower than the picosecond, that is about 0.3 picoseconds. So, you do not really see the overshoot effects. So, we just do not go into the discussion on the gallium arsenide at this moment. When I discuss gallium arsenide devices, I may bring this back. Let us focus on silicon, because we are happy with silicon devices and we are talking of small devices in silicon. Okay. So, the conclusion from this discussion is, in gallium arsenide FETs, the carrier velocity in the channel may exceed saturation velocity, because the collision takes place after few picoseconds due to the onset of ballistic transport and velocity overshoot effects for small even up to 0.5 micron channel lengths. In silicon FETs, ballistic transport cannot take place even when channel length is 30 nanometers or 15 nanometers, but that is estimated by taking such velocity 10 to the power 7, it will be lower than that. So, much smaller channel lengths are required to see ballistic transport or velocity overshoot effects in silicon. So, the drain current is limited by not by the saturation velocity, not by ballistic transport, not by velocity overshoot effect, but the velocity with which it is injected. Okay? That is, something else is controlling the injection velocity. So, at what velocity the carriers are injected? Okay? We will see what it is. I will not get down into the detailed discussion on that. So, drain current, if it is controlled by injection velocity, which is smaller than that velocity saturation, I can say that I can still write IDS is W q n at 0 into injection velocity, and that is lower than that. Then I will get the drain current, which is actually smaller than what you would get with the velocity saturation. But this injection velocity does not depend upon channel length, it would depend upon the conditions at the source end. Let us see what it is. I will not derive it, but I will just show that, because the deriving is bit of involved thing. There is a detailed paper written by Lundstrom and Wren on the physics of carrier transport in nanoscale MOSFETs, published in January 2002, in which what they have said is, when the carriers are injected from the source to the channel, okay, they are able to inject from the source to the channel by gaining an energy to raise above that barrier. Okay. So, they have got the thermal energy. In fact, they would be injected at a velocity close to 10 to the power 7 there. Okay. So, you would think that in the earlier analysis what we said is injection velocity is the thermal velocity. That is what you would get there at the point of injection, at the point when the electrons have just landed in the channel. But the moment they land in the channel, they start moving within a very short length, they suffer collisions. They suffer collisions, they start scattered backward. Okay? So, the average velocity of that beyond that point, within that short distance, is controlled by the scattering mechanism. Okay? I am not showing the derivation. So, that is controlled. So, if you go through the analysis, what happens is, if there is no scattering at all, you would have got the thermal velocity. Because of the scattering, the velocity of the electrons is controlled at that point by combination of this injection velocity or thermal velocity and the velocity with which it moves, that is mobility into the electric field. Velocity is mobility into the electric field, that is the low field. The electric field is not high at the source end, electric field high only at the drain end. Okay. If it is high, of course, saturation velocity you will get, it is not high. So, whatever electric field at E plus, 0 plus means just at the source end, that is the velocity that you would get. So, a combined effect of that, with skipping all the derivation, I would suggest that you go through this paper for that, because that itself would have taken me about half an hour to discuss that. So, injection velocity is controlled by these equations, that is thermal velocity, which is 10 to the power 7 centimeter per second. If there is no collision at all after injection, that would have been 10 to the power 7 centimeter per second. But because of the combined effect of the scattering, you get injection velocity less than the thermal velocity. You can see that if the mobility is very, very large, it could be that in that electric field, okay, you will have, it is like putting two resistors in parallel. The resistance is governed by the resistance which is lower. Okay. So, here if this is larger than this one, if the mu into E is larger than thermal velocity, we injection with thermal velocity. Okay. If thermal velocity is larger than the second term here, the denominator, injection velocity will be governed by this mobility. It will be actually combined effect. it will be neither this nor that. So, what turns out from that is, this is for the conclusion for this, our discussion is not ending here. Considering both these effects together, what you would say that you can still write the drain current is equal to W q into injection velocity. Injection velocity is the combined effect of these two terms. If I have high mobility in the channel, you may get thermal velocity itself very close to saturation velocity, but it will always be less than that. But if the mobility is low, then it will be far below the thermal velocity, saturation velocity. So, you can see that this particular term, drain current that you get, saturation drain current, will be in the very short channel devices are limited by the injection velocity, which is controlled by both saturation velocity or thermal velocity and the mobility. And you can see that both the terms which determine the injection velocity are independent of the channel length. So, injection velocity does not depend upon channel length. Therefore, if you are computing this current using the injection velocity, the drain current will be independent of the channel length. So, what we say here holds good. So, you get the drain current which is independent of channel length when you go to channel length which are 0.2, 0.1 microns length or below, but the current is lower than what you would get with the saturation velocity, because injection velocity is smaller than the saturation velocity. Okay? And this is actually, you can see the reference is this is a research scholar, modeling of nanoscale MOSFETs, PhD thesis of Stanford University 2002. There is a time when that model also was given by Lundstrom, etc., in the Purdue University. Okay. So, what is our aim from this discussion? What we see is you need to have very high mobility for electrons, because after all thermal velocity is fixed by temperature 10^7. You need to get higher and higher mobility. What is the way you can get higher mobility? What are the factors which affect the mobility? That we will see now. So, low field mobility should be high. The mu is actually the mobility in the low electric field. You go back to this, you see mobility is actually just the slope here, low field region. At the source end the field is low. As you go towards the drain end, the field becomes high. So, velocity naturally go up there. So, now going back to this, I am skipping all these things which you have discussed now. So, you are looking at either materials which can give you high mobility, or if you want to stick with silicon, what is the way you can increase the mobility? What are the factors which increase the mobility or limit the mobility? If you plot mobility mu n, this is actually mu, it does not show here, this is actually the arrow is mu, I think because of change in the program. This is the mobility is the y axis and the doping concentration. If you recall, to reduce the short channel effects, we always increase the mobility in the conventional MOSFET. So, if you increase the mobility, if you increase the doping, let me restate. In the conventional MOSFETs, you increase the doping to reduce the short channel effects, okay, and also reduce the oxide thickness to compensate for that. So, if you increase the doping, the mobility is almost flat. I have plotted this is actually approximated straight line. It will not be that straight, it will be smoothening here, smoothening here. So, when the doping is up to about 10^16, mobility of electrons will be 10,500 centimeter square per volt second. But once you reach about 10^16 doping, the mobility starts falling. Mobility starts falling because in the low doping concentration regions, the scattering centers are only lattice atoms. But when you go to higher doping, the dopants, they are in the ionized state. The ionized dopants give rise to additional scattering centers. The low doping mobility, they are not, there is scattering, but it is not high compared to the lattice scattering. But when you go to higher doping concentrations, additional electrostatic scattering due to the ionized dopants takes place, mobility falls. You can see the extent of fall in mobility. What was 1500 centimeter square per volt second can become even as low as 200. So, you can see if you take a look at those doping concentrations, this term, this is not 1500, this will be 200 when you go to 10 to the power 18. In 10 to the power 17, it may be about 600 or 700. Okay. So, moral of the story is you can't go to such high doping concentrations. In the classical MOSFET, you have to have high doping concentrations to reduce that short channel effects. Okay. What are the other factors coming into picture? The other factor which leads to reduction in the low field, and they say that field is actually along the y direction. But in the case of MOSFET, there is electric field in the vertical direction, there is normal direction. That is what we talked here was electric field in that direction. That is what we talked of here. Okay. Now, what we talk of here is there is also electric field in the vertical direction, the normal direction to the channel. So, electric field in the normal to the channel must be kept also low. But you know, when you make the oxide thickness small and the channel doping high, when you deplete the channel, there will be very high electric field. Oxide thickness is small, the depletion layer charge is high. So, QD by C oxide is the electric field, okay, or whatever charge is there, that gives rise to the electric field. QD by epsilon oxide, that is the electric field. Okay. QD by C oxide is the voltage drop across the thing. So, if the C oxide is large and if QD is large, or if QD is large, the electric field also becomes large. So, what we are trying to point out is, you will have, because of the high doping here and thin oxide, field will be large in the vertical direction. So, when the electric field is large in the vertical direction, the mobility of the channels along the y direction gets affected. Why? You can imagine when the electric field is in the direction, vertical direction like this, normal direction to the channel, if the electrons are moving in that direction, if the field is like that, it tries to keep it, hold it for a while in that region. So, there is a restraining force which keeps it back in that position. There is a qualitative way of understanding. That means, actually the mobility of the electrons moving in that direction gets affected if the field is large in that direction. So, you must avoid the field in that large in the x direction, normal direction. Now, an empirical formula is given by these people, Peccaroni and Warderman, in the year very way back in 1983 for the conventional MOSFETs. Mobility keeps on decreasing, mobility in that direction keeps on decreasing if the E x, we call it E effective due to including all the other effects. If that increases, that keeps on decreasing. So, what is the way you can do that? You can't help reducing the oxide thickness. You want to keep the capacitance large. What you can do will be reduce the doping concentration here. So, if you reduce the doping concentration in the channel, two things happen. One, the ionized impurity scattering gets reduced. So, mobility reduction does not happen. You can go to mobilities which are as high as 10,500 in silicon. If you use some other material, you can have mobilities decided by the mobility of that electrons in that material. Okay. And also, if you reduce the doping concentration here, the depletion layer charge gets reduced. Therefore, the charges in the depletion layer gets reduced, means electric field again is lower in this vertical direction, normal direction. So, if you reduce the doping concentration, naturally you will get improved low field mobility, low field in that direction, you will get improved mobility and you will get improved velocity. You can get very close to the saturation velocity, thermal velocity. So, the entire drive in the present day devices is to choose. So, these are the references which I am telling. So, to get high performance, what should you do? Just the last slide which I am discussing here today, which has got a lot of juice in that. Okay. So, high performance nanoscale devices therefore should ensure that doping is low, so that mobility is high. They should also ensure that the normal electric field is low, so that again the mobility is low field mobility is high. Okay. So, ultra short channel mobility devices with improved low field mobility is required for high performance nanoscale MOSFETs. You can't help reducing the channel length. Why should you reduce the channel length? You saw channel length divided by velocity gives you the transit time, higher frequency. To go to higher frequency, even though velocity gets saturated, because of reduced channel length, the time required for transport of carriers is reduced, so frequency is high. So, to take care of this aspect, ultimately to improve the mobility, new approaches are used. These new approaches are non-classical MOSFETs. Finally, we are getting down to what we wanted to discuss. So, they have emerged. These meet some of these things meet this goal of low mobility. Those devices are silicon on insulation MOSFET. If you recall, the MOSFET that you have got is whole thing is on a bulk region, and out of that we discussed right at the beginning, only the top layer is the one which is being used. Below that it is actually mechanical support. So, we can have silicon on an insulating substrate, a thin layer of silicon used. We will see how that works out, serves to improve the low field mobility. So, because of that you have got double gate MOSFET, ultra thin SOI MOSFET, silicon on insulator MOSFET and FinFET. These are the things which we discuss in the coming next few lectures. Okay. So, that is actually using silicon itself, and this trick that you are using in these devices is only the controlling the electric fields, controlling the dopants, which is enabled by the SOI device. But now, you can make use of the SOI device. In addition, you introduce strain along the channel. What is meaning by strain? If I have the channel, let me go back to one of those slides here. This is a channel. Now, along this channel, if I introduce a compressive strain in that direction, if I compress the channel in that direction, what happens is the lattice atoms are little bit brought closer together. So, if the lattice atoms are bit closer together, the collision distance becomes reduced. If the collision distance becomes reduced, collision time is reduced, mobility will be reduced. Okay. So, if I bring in compression, the mobility is reduced. But if I stretch it, if I introduce tensile stress along the channel, then the lattice atoms are slightly pulled. It may be delta, it may be fraction of an angstrom, like that. After all, distance is about 5 angstroms, maybe it is fraction of that. If you increase the length, the spacing between the lattice atoms is increased, collision time is increased, mobility is increased. So, in n channel MOSFETs, if I have tensile stress strain, if I can introduce, then the electron mobility will increase. So, whatever is good for electrons is bad for holes. Okay. Later on we will again discuss those details. In the holes, if I stretch it, even though the electron mobility increases, when you talk of these plus charges exactly offsetting takes place, I will not discuss that at this time frame. In fact, the whole movement takes place because of the jumping movement of electrons from bond to bond. So, the bond has to break and jump to the neighboring point. So, whole movement takes place by jumping movement of electrons from one bond to the other bond. So, if I stretch it, the electron has to jump on a longer path. That means, the whole movement will be more difficult if I stretch it. So, what we said is the electron mobility increases if I use tensile stress, but because of that the whole movement becomes difficult, whole mobility becomes less if I stretch it. How to introduce the tensile stress? I can deposit nitride on the top of the gate. That nitride has tensile stress, it will stretch it, elongate it. So, Intel has made some of these devices where they deposited low pressure nitride onto the on the gate over the gate to touch the channel, so that electron mobility can be increased. Okay. And the whole mobility can be increased by compressing the channel. How do you compress the channel? Take a look at this. By introducing nitride on the top of the gate, I can stretch it. I can compress it if I introduce germanium into the source and drain region. Source is silicon. During diffusion, you can add little bit of germanium also. So, this will be silicon germanium, small amount of germanium concentration. Germanium lattice or the atomic size is bigger than that of silicon. So, in these regions you have silicon and germanium atom at source end and the drain end. If you introduce, that volume increases, because radius of germanium atom is bigger. So, it is in the given volume you are trying to introduce dopants which are bigger. So, it tries to compress. I am sitting here, two fat fellows sit on both my sides, they will be compressing me. So, that is what is happening. You have germanium atoms added onto the source, that will be compressing the atom. So, if you do it for n channel devices, its mobility will decrease. For p channel devices, the mobility will increase. So, in the p channel devices, they add germanium to the source strain to increase the mobility. So, that is the strain layer. Okay. So, other thing is of course, totally use different materials like germanium. Leave silicon and go to germanium. Germanium has electron mobility which is about 4000 centimeter square per volt second, which is about 3 times, close to 2 to 3 times than that of electron mobility in silicon. Whole mobility germanium also is about 3000 centimeter square per volt second. So, both electron mobility and hole mobility are high. So, today people are talking of making devices on the germanium MOSFETs, and also in addition you can use gallium arsenide as the material for heterojunction devices. So, to sum up, what is being done is either go to silicon on insulator type of materials, that is non-classical MOSFET, or and use strain layers, or go to totally new materials like germanium or gallium arsenide to realize conventional type of MOSFET, but new materials. So, with that I conclude, and next session we will start with the non-classical MOSFET on silicon on insulator. Thank you.